you, Mr. Mehta. Yeah, it's a pleasure to be here. I come here periodically and give a seminar, but this time I'm going to do one study that I had done many years ago, and it is actually validating the previous paper which was presented here, which had used recent data and had numbers and conclusions similar to what I have achieved in this paper. No. So the topic is thorium utilization of fractional reactors and in cross-progeny fuel factors. And the cross-progeny fuel factors are introduced, and they are similar to what India is pursuing and wants to pursue further in any case, but I'll define them a little more in my talk. And this work was presented in a meeting or a conference between the US and Japanese workers on thorium a long time ago. And the calculations are also old, but the conclusions that I will reach here in this paper are the same that was presented in the last paper, which has used data and methods which are much newer, and they are similar, but there are much newer data available that is available to the people working in Kalpaka. So let's see how you. Okay, this little introduction. Thorium utilization thermal reactors and advanced converter reactors has been of interest for a long time. You know, since the start of nuclear power. I have worked on it many years ago, like 35 years ago, and that had presented papers at that time, and we're still doing the same thing, certainly. The main reason for that is that U-233 is a better fuel fissile material than the others which we have, which is U-235 and plutonium in the thermal spectrum. And it has a higher value of eta, much larger eta value than U-235 and U-239. So it's a better material. That one can achieve even a thermal breeder that was really aim for quite a long time ago. It was demonstrated in the United States with the construction and operation of light water breeder reactor at Shippingport, USA. It was a Navy project, and it was pushed by Admiral Rickover and Mr. Rudkowski, who was the physicist in charge. And this LWBR was a very special reactor, and it was a core with specially designed and with U-233 and thorium oxide in a PWR, and it was later, after the core was working for a year or two, it was the breeding was examined. It was established that one could get a breeding ratio of about 1.05 in the thermal spectrum. At that time, thorium was popular, and it was employed in the high-temperature gas pool reactor in Fort St. Vrain, and in the MSRI experiment Oak Ridge, and good performance and good conversion ratios were obtained. Of course, they were not breeders, but in these demonstration reactors, also thorium was a successful fertile material, and it helped in terms of achieving a greater conversion ratio than the uranium-238. Now, did this work, I presented this work in 1982. Fuel cycle characteristics and safety parameters of a plutonium, thorium fuel, liquid metal, fast breeder reactor. This was just the aim of this paper, and you'll see the results that we achieved at that time. And they're not any different in terms of general conclusions than what was presented in the last paper. The one thing which was really discovered in the application of thorium in the fast reactors was that that number one, there is a lower breeding potential, lower conversion ratio, and large reduction in the positive sodium void coefficient of reactivity. Now, that is the first feature is because of the lower fast fission cross-section, which is obtained in thorium than in U-38. But the second feature is very important for the safety of the element PR plant, and in particular for licensing of a plant, like a large plant of for example, 1,000 megawatt breeder I don't think it will be able to license with plutonium oxide and U-38 oxide, except when we do something differently before. And I have worked on that too. To reduce the sodium void coefficient, we have to put the fertile material in the core itself. And we have to have several subassemblies in the core itself, which reduces the sodium void coefficient. But you also have to put more enrichment or greater amount of plutonium in the core. So the inventory required will increase a lot. So this is a argument for using thorium along with thorium oxide, and you use thorium oxide, and you get much lower values for the void coefficient, and that is an issue which has to be tackled in licensing. But I think that is an important issue, and that's why the first reactor that the United States wanted to build, the twin silver breeder reactor, that core was changed for this reason, that the sodium void should be not negative but very small, and so that with the Doppler you could simplify that you get negative power coefficient, so that you do not get this pole disruption which occurs in postulated ion-based accidents for the pole like the loss of cooling exit. Now the symbiotic or cross-progeny fuel factors have been proposed, and the U-38 employed in existing LWR produces plutonium, which is then combined with thorium and burned in LMFPR to produce U-33, which is then employed in existing LWRs as a replacement for U-35. The use of U-33 in standard LWR increases the conversion ratio and decreases the apparent fissile material consumption by about 20%. So the breeding gain which is lost in LMFPRs is recovered by the use of U-33 in LWRs. This is a cross-progeny cycle diagram. We have LWRs, we have plutonium, uranium, thorium FPRs, and we also could have HTGRs and advanced thermal reactors. So we circulate we have to have both the reprocessing done for both uranium and thorium fuel reactors. That's for sure. That without that it doesn't work. If you can do that, then like India has at the moment, India is really the most well-placed country in terms of employing this cross-progeny cycles. Can't be done in the United States, cannot be done in Europe, and maybe Russia could do it, and perhaps France could do it, but not easy, because you have to have both the uranium and thorium reprocessing, And if you have that, then you can circulate U-233 to LWRs and take the plutonium out and bring it to the FBRs and then produce more plutonium, which goes back to the FBRs, but also some 233 can go back to the LWRs. So in this system, you do not suffer from any breeding loss, which is due to the use of thorium in plutonium, because you recover it back in the LWRs. Or PHWRs, it's thermal reactors. So also we have the option to develop HDGRs with 33 thorium fuel, providing much longer fuel cycle, thermal spectrum, ACRs, advanced conversion reactors could also be developed. And so the electric power generated per ton of uranium mined would improve substantially. This, as I said just now before, this cross-progeny fuel cycle requires the closure of both uranium and thorium fuel cycles so that plutonium and U-33 are available. The one-smooth cycles which are in LWRs will not be sufficient. So thorium fuel cycle was closed for the reprocessing of LPWR fuel, but not much has been done after that. And so it's a big issue because the thorium fuel reprocessing would need shielded facilities due to radiation from the daughter products of U-232. So you have to develop those before you can make a claim, yes, I will do cross-progeny fuel cycle. So this paper employs the calculations and their results obtained many years ago. I'm sorry for that, but I see that the current calculations which have been done in Kalpakam are backing them up. That's why I say these results are still valid. The cross-sections certainly have changed, but the changes in cross-sections do not affect the general results that I obtained here versus the results obtained in the previous paper. So thorium can be employed in the form of mixed oxide, mixed carbide, and metal alloy fuel in a thorium element PR. Now, thorium oxide to thorium oxide is similar in physical properties to UO2 fuel. Actually, thorium oxide to thorium oxide has higher conductivity and melting point than the UO2 or the fuel. So the performance of this should be at least as good as that for the UO2 or to fuel used in NFFPR. Now, the other form of use of this in reactors is the metal alloy. And this was studied a long time ago in Oak Ridge. So key material and thermal properties were measured, and I guess they had been measured here too. Phase diagram, thermal conductivity, density, and fabrication potential. Small sample heating were also done a radiation test was performed to establish swelling rate. So this thorium plutonium metal fuel has reasonably high melting temperature, limited swelling rate, and relatively mild failure rates. That with this we feel that it's a good material and for to be used in the fast reactors, just like the metal metal fuel was employed for EBR2 reactor, and that worked for many years and achieved high burnup. And so the sodium bonded thorium plutonium metal fuel is also effective as the fuel was in the EBR2 fuel. I worked in EBR2 for 6 years, and we developed a real good idea there that to provide some space for the metal to expand inside the clad. So once it expands, then it doesn't put pressure on the clad material bad, and it behaves very well for long-term burnout. The same idea can be applied in any future application of metal fuel in a operating element here. Now, I'm going to give some results of calculations which, like the ones which are presented last time, in the last paper, is similar. Thorium-based fuels considered the three oxides. Thorium oxide is 35 oxide, thorium oxide to 33 oxide, thorium oxide, plutonium oxide, and metal alloys, and which included those with plutonium generated in LWRs containing about 60% plutonium 39 and 241 of plutonium, 21% plutonium 40 and plutonium 241. And radial blanks we use were thorium oxide, uranium oxide, thorium metal, or uranium metal. So it's a study which employed different possibilities, and we performed fuel cycle calculations with an 8-group cross-section collapsed from a 29-group cross-section, which was obtained from end of data to the ANL code MC square, which is a for fast react calculation code. And the cross-sections were generated critical buckling for the core region, other region that's 0. And for Doppler coefficient, to cross-sections of 700K and 1200K with 7. So we've done the homework as usual, and we employed the codes that were available then, and they are similar in their methodology that's being used now. One was a full cycle code, a Rebus, and then there was a 3D diffusion 34 citation. The results of calculation are in the next table. The reference UO2 PUO24 is case 9, and I come back and tell you the main results. It's a long table with much data, and basically it's clear from here that the inventory is going to be high when you use thorium. Like in the total core fissile mass for thorium oxide, due to 35 oxide core, you need 3,900 kilograms. But when you go to 233, you drop to 2,500 kilograms. When you use plutonium, it's in between. So it's also you have to figure out how much material you have to start a new core. So this gives you an idea where you need more fissile material than the other cores that you have. There's some there's fissile production or fissile absorption ratios here, and they vary from 0.84 with thorium oxide to 35 UO2 core, number 1 case, versus 1.31 for the number 7 case, and the UO2, and then 1.39 for thorium 233 plutonium case. So there's a variation, but I think the basic issue which I'm going to treat, which I'm going to hammer on, is the safety of these reactors and lessons. The distribution of sodium wildwood was calculated. Let me go back here. The comparison, the case 9 depicts penalty in breeding ratio with thorium-based oxide fuels. The penalty disappears with the use of metal alloys due to 33 fuel cores do not display breeding but conversion. The most outstanding feature of thorium fuel cores is a very marked reduction in positive reactivity coefficient for sodium voiding from the core. The whole core voiding coefficient is negative except for plutonium oxide, thorium oxide fuel core. And the Doppler coefficient is sufficiently high, negative for thorium-based fuel, so that a core with negative sodium void and Doppler coefficient will not suffer anergetic dispersal during the initiating phase of the hypothetical accidents which are in the licensing preparations. Distribution of void work was calculated, and that's shown in this table. The F curve, that top curve is the UO2, PuO2, plutonium oxide, uranium oxide, and that's plotted with a factor of 1/2, so it will be double, like 16 will be like 17 will be 34, versus D, which is Thorium-33, and that's just like about 2, 3. So a factor of 8 to 10 in the sodium work coefficient at the center of the core. And so this is a huge change, and there's a huge advantage in terms of safety of the fast reactors if you have thorium mixed in rather than U-38 mixed in with plutonium. So that's the major point of this paper, that for licensing purposes you need to have this kind of safety margin which destroy. It's the same kind of issue which destroyed that Chernobyl, because they had a positive void coefficient in the core as the water was boiling away, and the reactivity was increasing rather than decreasing. And that's what the same thing one has to worry about in sodium. But of course, it's much higher temperature when sodium starts boiling, but it doesn't matter. Once it starts, it can go up very fast after that. So it's only when boiling takes place in the inner core region that some positive reactivity addition may occur. If you have a thorium in the blanket as well as in the core region. And if you have thorium metal blanket, it increases breathing gain, but plutonium-239 is produced instead of 233. Blanket material does not greatly affect the reactor physics parameters. That's what the point was made in the last paper too, that the blanket does not really affect the core physics parameters. This is one curve. This is the other one, which is along the actual height, and here also same kind of results, that we really do not get much of a sodium void, except nothing negative, except for this little part here. But we have negative Doppler coefficient too, so that overpowers it, and so we will not have any kind of a kick which would drive the fuel out of the core and disperse it all over in the vessel and maybe outside the vessel. The cross-progeny cycle to employ 33 producing thorium fuel LMFPR in the currently available NWR. The straight replacement of 235 by 233 reduces the total fissile inventory. The calculations we performed showed that you can go critical with 2.44% fissile content versus 3% with 235. So the U233 is about 20% less in the volume, in the amount required. The integral conversion ratio also the 235 fuel is larger by it's about 0.75, it's 25, it's still larger than that in the 235 fuel core. We can also think of THWR, the kind of reactor 33 feet and thorium oxide fertile material can reach sufficiently high conversion ratio that the fuel cycle may become self-sufficient. Now, I think when we think about putting thorium oxide in THWRs, one needs high enrichment, and one can supply it also with 235 to start with, but 233 starts building up and then compensates. And so this it's a good idea to think of having some 235 in the PHWR to get it going, and then 233 keeps coming in, and then finally you get a self-sufficient system in time in PHWR. PHWR is very good compared in this sense from the light water reactor. Now this business of this special feature is the UT32 production, which is quite a lot of gamma rays coming quite close to 6 MeV, so you need remote handling and shielding of recycled fuel in the case of thorium use. This complicates the fuel reprocessing and refabricating of 233 containing fuel will be more expensive than the reprocessing of 235 plutonium fuel. But that's a special feature. Another feature is the production of 233 protactinium, which decays into 233 with a 27-day half-life. The shutdown reactivity requirements will be much higher in this case. Third is the delayed neutral fraction beta of 232 fuel is less than that of plutonium-38 fuel. This affects the reactive period and beta power increase below from critical, more stringent operational controls will be required. For example, lower for control rod and slower withdrawal, but faster insertion rates will be needed. So this applies to also fast reactors fueled by 233 or plutonium 239. 239 is similar in terms of the beta of the plant. The other point I wanted to make that we have a lot of plutonium sitting around. I just learned yesterday that 140 tons of plutonium is sitting in UK because they were reprocessing for a long time. So they reprocess the weapons material, and then they reprocess from reactors, and so there are 140 tons of this plutonium is sitting, and it's it's a store, represents a huge amount of nuclear energy stored, but not produced. The best way, this is not the best way to extract energy from stored plutonium with recycling thermal reactors, but with recycling fast reactors with thorium fertile material. I think this would transmit plutonium from LWR into U-33, which could be used further in LWR's considerable advance. So the nuclear utilization efficiency will be enhanced considerably, and the stored plutonium flux will be reduced effectively, and thorium, a fertile fuel, will be brought into the nuclear economy. Because I don't think any other country is going to bring thorium into their economy soon, unless they get some kind of a advantage of this. And the advantage I can see is if we can get this plutonium just sitting around to start the reactors on plutonium, thorium, and the best would be to use it in fast reactors, and that way you produce 233 for LWRs for future. Now I have extolled the virtues of thorium in nuclear power economy through its employment as fertile fuel along the fissile fuel plutonium 239, which is obtained from LWR or from storage. And that implies that the Gen 4 nuclear plants will be deployed in reasonably near future. This will not happen in many countries, but could happen in India, France, Russia, and perhaps USA. It can be argued that thorium use, as explained in this paper, may facilitate the introduction of LMFPR as a Gen 4 plant, because they still are not really keen on bringing LMFPRs. Japanese have the LMFPR, but they have shut it down. Only country which is using LMFPR right now is Russia, and India is going to start. But the cross-progeny fuel cycle could also serve as an attractive feature, since the decrease in nuclear economy suffered with thorium LMFPR should be recovered V+53 in end of the earth. That it would need development of reprocessing facilities for uranium and thorium fuel cycles. These facilities would have to be safeguarded and secured. That I think is finished. And the U232 is an advantage in terms of proliferation, but that diversion. But we feel that the diversion resistance of fuel cycles cannot be exactly quantified, and the exclusion of the technologies of LMFPRs and ACRs based on proliferation concerns, I don't think it's justified. The summary is that we have discussed the thorium-based fuels application in fast-period reactors. The fuel of choice for LMFPR should be plutonium-thorium metal alloy, because this essentially will preserve the breeding gain obtained with plutonium oxide, U-38 oxide, while reducing the sodium void coefficient from about $10 to about $2. And that licensing exigencies would require including, otherwise we'll have to put some fertile material in the core of 1,000 megawatt LMFPR in some distributed form, which will increase very substantially the needed fissile material plutonium criticality. Also, you can't really do it so well because that material becomes more power producing later as it increases in terms of making its heat generation with the fissile material plutonium. And so this makes it much more complicated for design with some orifices and so on, which is much more difficult. GCFRs and SDRs could also become an option with thorium fertile material, and they have operated in the HPGR successfully, but GCFR has not been so far. And the GCFR, the thorium blanket, produces large quantities of U233, and I showed this in this table that the thorium blanket on a GCFR produces 410 kilograms of U233 in 1 year. So this is a good producer of U233. But I'm not pushing GCFR because they don't really have a really peak capacity which is fluid like sodium provides. So it's a long shot. And this is the HDGR also can be designed to have low inventory if you sort of design it with a conversion ratio of about 0.9 to 0.94, and that really decreases the requirements for the fissile material. So finally, coming back, I think the introduction of thorium in the Indian program in fast reactors should be earlier than later. I think we should not wait, and I think it would be actually demanded by the licensing authorities, because a core disruption accident in a LMFPR is a very bad accident, very bad accident. So you really have to have some kind of a way to reduce this possibility, and you need to tell the people that this is a safe reactor, and you will not have any chances of release of radioactivity in the air because of any kind of accident. That was my pitch. Thank you very much.
you, Dr. Sehgal, for taking us a long journey. From there, the various limitations and the new thing that's coming up. The last point that you have made, I would like India to make a comment on that. Would you like to say anything on that?
Yeah, I think I welcome his statement that with the approach that we have in currently thinking about that. So probably we should look for ways of introducing the thorium blanket at the earliest in the renewable system. Of course, other issues can be tackled, other solutions could be found. That's what I feel. Okay, probably add strength to our position. So, can I have one question?
Yeah.
It relates to maybe rather not questions, but opinion. See, when we discuss about the new reactors designs in the future, especially after the post-Fukushima and the emergence of the Gen 4 systems, the Gen 4 safety criteria in almost all the countries, and also in IAEA level, very stringent things are being imposed, especially with the sodium coefficient. Either 0, negative, or 0, or maybe a little positive, which is what people have been talking about. But at the same time, there is another school of thought that don't worry about the sodium coefficient, it will be $5, $6, $7, whatever it is. But we worry only about the energy release. Energy release. As long as the energy release is going to be small or contained, is not a problem to be worried about. We don't worry about the sodium coefficient. This is one school of thought. And maybe I can give an example. Of course, many countries are into the design of new sodium fast reactors. And the example of Japanese is that GSFR, currently they are designing 1,500 megawatt electric. And of course, the French is also designing 600 megawatt electric Astrid in Europe. But the approach is quite different. Astrid, they are going for either 0 or maybe small positive. But they have been varying the statement, maybe they may go for negative. But in the case of JSFR, they are right from the beginning, they are maintaining more than $5, $5 to $7 in fact. So could you comment on the second school of thought regarding the energy release?
Yeah, I think, leak is an issue of the actual manufacture. And I don't, if it's a large leak, that's lots of sodium, but if it's sodium fire that you can have, that's the issue of the leaking sodium. But coming back to the accidents where you can have a core disruptive accident, because the fast reactor core has about 5 to 6 times critical mass, and so if that happens, you disrupt the core, and the fuel has to come off of the core, otherwise it will shut down. So it has to disperse the material. In that sense, if any material disperses like in Chernobyl, God forbid this is an accident in India with such large populations, forget it. If I were on the I would recommend this kind of.
Similar to Japan, of course, Europe, though they are going for negative sodium coefficient, but some papers or some studies, they still maintain that as long as the design is able to show that the sum of the reactive coefficients remain less than $1,
exactly.
The Pratt-Newton critical.
The power coefficient is negative.
We should worry.
But you cannot actually really certify a core expansion coefficient, and because you can measure them later, but you cannot certify them initially. I mean, I was in the design team for this reactor that built in France. Basically, they found that they had a very nice negative coefficient for core expansion. It was accurate, and regular expansion. But they couldn't certify it before, but they built it with that positive sodium water coefficient. They went ahead, but you know what happened? They shut it down now. after they had a leak, and the leak was not the only reason. It was the protest about them, the whole reactor design that they had to shut it down. It went for only 3 years. Particularly in future, you will be building big plants, yeah.
Thank you.
Well, in absence of other French colleagues, I was a previous director or DRE and involved with the Astrid program, so I can add some elements. So in the last 2-3 years in France, CEA, Arriva, but also EDF, we worked on Astrid. And one of the key aspects was indeed to have a negative void coefficient. And we went to a very special core, which is quite complicated from the fuel cycle because it's a very heterogeneous core, obviously, which is called CFV, it's version 2, which I do have a slide over here, which it currently has a negative 0.5 to minus $1.5 void coefficient, okay, throughout the core. Now, the reason why it took that much years because the licensing authority makes reference to the LWRs today because in the Gen 4 context, whatever kind of reactor, you can't be worse than what is doing ongoing today. And the licensing authorities will in 10 years or 15 years or in 20 years always compare what is the current practice at that moment. And that is negative void coefficient. And unfortunately, that pace, that cost, that complicates design of an Astrid and the design of the core and complicates the fuel cycle associated with it. Because, you know, with a positive void coefficient, non-acceptable at all, but your fuel cycle and reprocessing is a lot easier than with, you know, a negative void coefficient fast-reactor core with a very heterogeneous actual fuel assembly, which is complicating recycling plutonium management quite a lot.
And the beta is 0.3%. Yeah, so you go from critical in 1.03. 1.003. Yeah.
And like Professor Sehgal was saying, you know, the experience of Phoenix and Super Phoenix. Obviously in France, those were closed, call it, on political technical regions and technical small and political high capital. Okay, but you can't repeat in this kind of country, and surely not in Europe, you can't repeat this kind of story. So, unfortunately, we are forced to provide a Gen 4 Astrid concept which is safer than safe. Otherwise, it won't fly.
I wrote the first paper in the US on how to reduce this sodium void coefficient in a regular plutonium oxide, uranium oxide. You have to input fertile material inside the core. And the fertile material starts producing plutonium, then how do you, it starts making more heat. How do you do that then? Yeah, I mean you have to orifice this core, these regions. And it becomes a very complicated core design and also takes much more inventory.
Okay.
Very nice talk. Thank you for the very informative talk. And I had spent my first 18 years in the cost sector group at Progeny, day in, day out, Dr. Lee, Dr. Franjit, we used to discuss all this. One point I would like to ask your advice is, you are talking about this sodium void effect. Is it at zero burn-up or higher burn-up? So what is the burn-up profile of the sodium void activity? Because it becomes sometimes more positive as this burn-up. So it is not that you work only with the one particular state of the reactor at zero burn-up. You would see the entire burn-up period and see that the parameters satisfy your safety criteria.
Okay, I think in this table I have the number of days cycle length of 223 days to 61 days.
Okay, look at it.
Can we discuss over the
One more small thing about the nuclear data I also mentioned to you. I just want to make a comment. When you use the old calculation and the new data sets, new codes, they agree at zero burn-up. But as you go away from the zero burn-up, it changes. And also, there are lots of cancellation of other errors. So isotope by isotope, you substitute, things change drastically. This we can discuss later.
Included in this document.
Okay, I think we discussed it in that one. Thank you very much. I mean, last Friday, I measure, thank you personally. Without momentum, which is already.